Well, g'day. Welcome to our discussion today of quadratic functions, section 2.4. In the previous section, we discussed linear functions. Today, we're going to talk about quadratic functions. Then we're going to talk about piecewise functions. So in 2.1 and 2.2, we introduced the basic properties and ideas of functions. And now we're introducing special types of functions. And then the next chapter, we're going to generalize these to polynomials. So our topic today is quadratic functions. These are functions that have a highest power of 2 in their expansion. So we've got an ax squared plus a bx plus c. The a, b's and c's are just real numbers. A is not 0, because if a was 0, then that term would not be there and it would just be a linear function. So a is not 0, but a, b and c are just some real numbers. So let's start with an example of functions that are and aren't quadratic. So here are a bunch of functions. I recommend you pause the video for a second and just look over the functions and decide which of them do you think are quadratic and which do you think are not quadratic. All right, so hopefully you've paused and you've got an idea. This first one, well, clearly it is. It very directly matches the definition here. A is 3, b is -2, c is 1. This first example is quadratic. The second one doesn't look like our definition, but we can easily use some algebra and expand that out and make it a quadratic function. So if we expand this, we're going to get something like that, which we can then expand to 2x squared, what would that be, plus 2x minus 4. And that very much is of the form of a quadratic function. So again, this definitely is. A is 2, b is 2, c is -4. The third one, if we thought about expanding that out, well, if we expanded out the bracket in here, we're going to get a 2x squared plus some other terms. And then when we multiply those, the leading term in this is going to be 2x cubed, and then some other terms. So clearly it's not quadratic, because the quadratic has the highest term of x squared. And we've got an x cubed here. So this third one is not a quadratic. Fourth one here, part D. Well, that is a quadratic. A is the square root of 2, b is 0, c is negative the square root of 3. Those numbers are clearly real numbers. That's a real number. There's no x term, so b is 0, and c is minus square root of 3. Those are all real numbers. So this fits the model of a quadratic. So this third one, part D, definitely is. Similarly in part E, again, it doesn't look like the definition up here, but we can expand this out. And if we expanded that out, completing the square, we would get a term that looks like a quadratic. We'd multiply by 2, subtract 1. When we expand all of that out, we definitely get a quadratic in the standard form that we've got up there. Well, not the standard form, but in the form that's up here. So again, this is a quadratic, even though it might not look like it. And this is actually written in what's called the standard form. And we're going to talk about that in a little bit. So contrast it with anything that can be written this way is a quadratic. And we're going to call something that's written like this as a quadratic written in standard form. All right, what about f? Well, if I expanded the top here, I'm going to get a second degree polynomial. I'm going to get a term with x squared as the highest power. And then I'm going to divide by x. So it's going to have x as the highest power when I'm done, probably with a 1 over x kind of term. This is not a quadratic. One way of looking at this is to say, well, the domain is all of x except 0, because you can't divide by 0, and so 0 is not in the domain. So this doesn't match the domain of a polynomial, because every polynomial's domain is all real numbers. Same argument with this last one. I could factor out an x here. All right, this is 5x cubed plus 4x plus 1, and then we're dividing all of that by x, and you might say, okay, well, those x's are going to cancel. I can cancel these x's, and that's going to leave me a quadratic. I'm sorry, that's clearly a 2. That's going to leave a quadratic, but it's not, because this function has a domain. Well, it has the same domain as the last one. The domain is all real numbers except 0. So it doesn't have the same domain as a quadratic, so it can't be a quadratic. So hopefully that gives you an idea of the kind of functions that are quadratic functions. Okay, so our next example is to sketch this quadratic. We've seen that something of that form is a quadratic. We could expand this out. This is 3 lots of x squared minus 2x plus 1. Just multiplying this out, and then we're adding 2, and then simplifying that whole thing we'd have 3x squared minus 6x, and then we would have plus 3, and then we're going to add 2 more, so plus 5. There we go. Not very well written, but that's clearly a quadratic. But the original form is much easier to sketch because we can use the ideas from the previous section. Okay, so here we've sketched the standard power function, y equals x squared. And if we look at this original form that we had, this takes the basic power function, moves it 1 unit to the right, stretches it by a factor of 3, and moves it up 2. So I've added to the picture here the parabola shifted 1 unit to the right, y equals x minus 1 all squared, and then I've multiplied it by 3, so every y value gets 3 times bigger. So the y value here is now 3 times bigger right there. So this is a vertical stretch by a factor of 3, and the last thing to do is we're going to add 2 to the function. So we're going to move it up 2. So let's say this is 2 there. So let's say that's 2, I don't know, I'm making that up. So let's move the graph up 2 units. There we go. Move it just vertically up 2 units, and that is our final graph. So the function that we wanted to graph is this final graph here, where the point down here is called the vertex. So the vertex is that point that was at the origin on the original graph, y equals x squared. This is the vertex of y equals x squared, and for our new function, the vertex is moved here. So it's moved 1 unit to the right, 2 units up, it's at the point 1, 2. Okay, well let's generalize this idea to standard form. Okay, so the standard form of a parabola very much matches the original example we have on the page here. We had 3, just rewriting that original equation we had, we have 3 lots of x minus 1 all squared plus 2. And this is written in standard form. And if you compare it to the more general thing I have here, the 3 is the number a at the front. We've got the number 1, which we're going to call h more generally, and we're adding 2 at the end. So all the squarings going on of this x minus h term. So we had x minus 1 all squared. So this is in standard form, and things in standard form are very easy to sketch. So let's have a go at another example. Okay, so here we have an example. It's clearly in standard form. The a is minus 2 here. The h would have to be minus 3. The k is negative 5. So thinking about the rules of transformations of functions from the previous section, we're going to take this basic, oops, that's clearly not a parabola, let's try again, there should be a square there. We're going to take this function and we're going to follow the transformation rules. So to begin with, we move 3 units to the left, which moves the parabola to here, to minus 3. If you think about the vertex, this is what we call the vertex. So we move the vertex 3 units to the left, to minus 3, and then we're going to scale the parabola by a factor of 2 and reflect it around the x-axis. And then we're going to move the whole thing down 5. So if I just do those first 2, we're going to have a parabola that looks very much like this. So it's stretched. So it's stretched vertically, it's moved to the left 3, it's stretched vertically, and then it's flipped around the y-axis. And then, so this one I've drawn so far would be a sketch of something like this. And then the last job to do is sketch the final product, and the final product is where we have the minus 5. So that moves us down, we're subtracting 5, so we move down to minus, not minus 5, but minus the square root of 5, and so we end up with a parabola that looks something like this. And this point here is called the vertex, and the vertex is at the point minus 3 minus the square root of 5, because we thought about how this point moved. It moved 3 to the left, and then it moved 5, square root of 5 down. And that gives us the location of the vertex, because we knew the vertex here started at 0, 0. And that tells us something about the general form, because let's go back and look at the general form we have up here. H was minus 3, that's how far we moved to the left. K was negative root 5, and that was the location of our vertex. So that tells us something about the standard form, which is where the vertex is. The vertex is always at the point hk. So this standard form, we can just read off the vertex. We can immediately look at this and say the vertex of the parabola will be at minus 3, negative root 5. There's one other thing we can read off, and that's the y-intercept. It's not so clear on this one where the y-intercept is, but you can see it's going to happen somewhere down here. And to find the y-intercept, we just plug in 0, right? So the y-intercept, we plug in x equals 0. So f of 0 in this case is going to be minus 2 lots of 0 plus 3, all squared, minus the square root of 5, which gives us, well, this is 9, so this is negative 18, and then take another square root of 5, or whatever that is, but that will be the location of the y-intercept. So the y-intercept is at the point, well, it's on the y-axis, so it's where x is equal to 0, and y in this case is not a nice number, but we can calculate it. All right, that we can't read directly off this form, but we can read the y-intercept off the other form more simply, because if you think about plugging y equals 0 into sort of this equation, sorry, x equals 0 into this equation, these first terms drop out and the y-intercept must be at 5. So the y-intercept is something that we can easily read off the equation when it's written in the ax squared plus bx plus c form. The y-intercept is very straightforward then. If it's written in this thing we're calling the standard form, then it's really easy to read off what the vertex is. And so those two things have their advantages, and you can easily see you can take something that starts in the standard form here and expand it out and turn it into this ax squared plus bx plus c form. And we can also go the other way. So we can start with that form and turn it into standard form, and that's our job next. Okay, so we're going to take a new polynomial and we're going to write it in standard form. We're going to take 2x squared minus 12x plus 10. This is a quadratic written in the ax squared plus bx plus c way, and we want to write it in standard form. And we're going to do it by leaning on the example we had on the previous page where we actually went backwards, or the opposite direction. We started with it in this standard form and we turned it into the ax squared kind of form. So I'm going to take this and write it on the next page just so we have it to sort of refer to. Okay, so on the right here you can see this transition from the standard form into the ax squared kind of form. And I've written it out in great detail here where we interpret what this squared means. It's just these two linear functions multiplied together, so we expand them out. That's actually a perfect square, right? Because I can take this and write it as x minus 1 all squared. So the key here is that there's a perfect square lurking in the middle. How did we make the perfect square? Well, if you think down here, the first thing we did, I'm actually thinking about moving backwards now, moving from the bottom up. First thing I did was kind of pull the 3 out. And somehow I got a perfect square here. And that's the key. So let's go back to our example. Our example in this case, we've got the function 2x squared minus 12x plus 10. And the first thing I'm going to do is, looking at this, I'm going to pull the 3 out. And then I'm going to hope for the best. Well, in this case, I pulled the 3 out because it was multiplying the x squared. Here I've got a 2 multiplying the x squared. So I'm going to pull the 2 out. X squared minus 6x. Actually, I'm going to leave the 10 alone. I'm just going to leave the 10 hanging. All right. So this is the same polynomial, but I'm starting to reverse the thing that I had going that way. And the goal is that I want this thing in the brackets to be a perfect square. All right, so if I want this to be a perfect square, then I'm going to come down and I'm going to say, well, what does a perfect squared look like? If I've got a perfect square, let's write it as x plus a, all squared. If I multiply that out, expand those brackets, it's x squared plus 2ax plus, well, a squared. There's our perfect square. I've got x squared minus 6x up here. I'm comparing with x squared plus 2ax, so the a must be, well, half of this number. So in this case, minus 6 over 2. So the a value here must be negative 3. Where does that go? Well, it goes here. So we end up writing this as x squared minus 6x. I'm going to leave that the same. And in fact, I need more room, so let me just open up some room here. I've got x squared minus 6x, and I want this to be a perfect square. There's a plus 10 at the end. To be a perfect square, x squared minus 6x, I must have a plus a squared. Well, a was negative 3, so we must have plus negative 3 squared, which is 9. But I can't just add 9, so I need to take 9 away as well. So just rewriting this, this is 2x squared minus 6x plus 9 minus 9 plus 10. And the key here is that this piece is a perfect square. And that's what we were looking for. If that's a perfect square, then I can rewrite that whole line as 2 lots of, well, that orange box is going to become, it's a perfect square. A was negative 3, so plugging that in here gives us x minus 3 all squared, because it was just x plus a, and a was negative 3. So x minus 3 all squared, that 9 is still there, and then we've got plus 10. And so expanding this out, we've got 2 lots of x minus 3, all squared. I'm expanding the 2 in now, distributing the 2. 2 lots of 9 are 18. Then we're adding 10, it was just observing. So 2x minus 3, all squared, minus 18 plus 10, that's negative 8. All right? So there is the standard form for our original quadratic. And given we've got the standard form, we can very easily plot the graph because we know where the vertex will be. The vertex is going to be at the point hk, which in this case, there's h, it's 3. There's k. In this case, k is, well, negative 8, because remember our standard form was ax minus h all squared plus k. So k is negative 8, h is 3. That's where the vertex would be. If I sketch this quadratic, we're going to have a vertex at x equals 3, y equals negative 8. A is positive, and so it's going to open upwards. It hasn't been reflected around the axis. It's been stretched by a factor of 2. What's the y-intercept? Well, the y-intercept is very easy to find from the original graph, because the y-intercept up here is when x equals 0, the function is equal to 10. F of 0 is 10. So another way of saying that is the y-intercept is the point 0, 10. Don't know what happened there, but it's the point 0, 10. And so the point 0, 10 we can mark on the axis up here. There's 0, 10. And so the quadratic must look something like this. Vertex at 3 minus 8, y-intercept at 0, 10, and we've got a pretty good graph. So this standard form idea lets us sketch the graph, but lets us find the vertex very easily, and this idea is called completing the square. So what we did was complete the square, and that's the key. It's that operation in the middle here, where we take this thing and we turn it into a perfect square by adding and subtracting the right number. And that number was negative 3 all squared. That's coming from here. We need the negative 3 all squared. Okay, so let's finish up today by just summarizing what we've seen. We started by introducing the idea of quadratic functions, which have the form ax squared plus bx plus c, and we showed that we can convert to and from a standard form, where we introduce these numbers h and k. And if we consider our example, which is just coming from the calculations we did on the previous page, we can see that actually the a remains the same. From the process we used, we must have, in fact, the same values here, and so that's why these two are both a. They're both the same. The b and the c that are here in the example, they're going to change, they're going to be different from the h and the k, but the a out the front remains unchanged. Okay, so we saw an interpretation for the h and the k, which is that it gives us the location of the vertex. So the vertex on the parabola that we draw is going to be at the location hk, where that's coming from our completion of the square. That's coming from the work we did on the previous page. And the example I've drawn here has a greater than 0. There's no reflection around the x-axis, and so the parabola opens upwards. And we get in the center here what's known, going through the vertex, what's known as an axis of symmetry. That almost goes through the center. So here's the axis of symmetry because if we reflect the parabola through that axis, we get the same thing on each side. So this is reflection symmetric across that axis like a mirror, or at least it should be. The y-intercept, that's easy to solve if we have the parabola given in the original quadratic form, because it'll just be the c value, whatever c is. For in our previous example, that was 10. So that will be the y-intercept. So we can read the y-intercept off here. It'll be at 0c. To find the x-intercepts, we've got to do more work. We've got to solve f of x equals 0, just like we talked about in the general case. So this is pretty much the picture we have of parabolas. We'll talk more about parabolas in the next class, but in the meantime, have a go at the introductory problems and the quiz, and I will see you in class.